Hello guys, welcome to my channel. So in the last video of this series we talked about Spring Boot interview questions, and in this video we are going to talk about microservices. So if you haven't seen any of the videos in this series, do take a look at my YouTube channel. You will see all of the videos there which I have uploaded for this particular series. Now if you haven't yet subscribed to my channel yet, please do. It's a simple thing and it's a humble request that please do that. Now let's kickstart this video. Alright, so let's talk about microservices now, and the very first question: what are the key principles of microservices architecture and how do they differ from a monolithic architecture? So we have single responsibility principle, we have decentralized governance, we have independence, API first communication, data decentralization, scalability, fault tolerance. I can go on and on. So these are the key principles that we have in microservices architecture. So let's talk about it. So single responsibility principle comes from your solid principles. So if you know about it, that's the first principle from the solid. So it means S means single responsibility, which means that each microservice is designed to perform a specific well-defined task or a business function. So this ensures that services remain small, focused, and easy to understand and manage. Now decentralized governance, so here teams have the autonomy to choose the best tools and technologies for their own microservice, rather than adhering to a one-size-fits-all approach. So here it promotes innovation and flexibility across teams. So if you have two separate teams and they both are working on their own microservices, then it doesn't matter which tech stack they are using, they can use whatever they want. So this gives you independency. So that is our next principle, which means that services are loosely coupled and can be developed, deployed, and scaled independently of one another. Now failure in one service does not directly impact the availability, but we will talk about it later. Now API first communication. So services communicate through well-defined APIs, like we use REST. Now direct access to a service internals by another service is prohibited. Alright. Now data decentralization. So each microservice owns its own data with no direct sharing of databases between services. So this encourages a database per service pattern for better independence and scalability. Now scalability, services can be scaled independently based on their specific load and uses patterns. So this enables efficient resource utilization. And any point of time, you can increase the scalability or decrease the scalability. Now fault tolerance. So the architecture is designed to handle failures gracefully using patterns like circuit breakers, retries, and failover mechanism. So this comes under when you talk about independency, like I was saying earlier, failure in one service does not directly impact the availability. So when you use fault tolerance, so this promotes a resilient system that minimizes downtime. So here you can make use of circuit breaker to enhance the functionality and take care of your faults. Alright. Now we have DevOps and automation, then component per service, then event driven architecture, technology diversity, security, and these are the key principles. Now let's talk about the basic difference between microservices and monolithic architecture. So this is a very basic question for sure, and I think many of us know about it, but just to summarize, monolithic architecture means a single unified project or a code where all components are tightly coupled or integrated. So here you have your UI, business logic, and database inside a single code. And this project or code gets deployed as a single application, often as a single binary or var or jar file. Right? So this is your monolithic, but the picture is different in microservices. Here the system designed as a collection of small independent services, each responsible for their own specific business capability. Now here we deploy each application independently, and here the services communicate via API or messaging. So here you can deploy, develop, scale every service independently. So here you have more freedom, because here you have loosely coupled services. Alright, so this is the basic difference. Now let's move on to the next question. What are the pros and cons of synchronous versus asynchronous communication in microservices? So let's first talk about what is synchronous and what is asynchronous. So synchronous communication means that the sender waits for the response from the receiver before proceeding further. So here the example is your REST API call over HTTP. But in asynchronous communication, the sender continues processing without waiting for the response from the receiver. So here you can use any queue, message queue like RabbitMQ, Kafka, right? Now let's talk about the pros and cons. So first let's talk about synchronous communication. So the advantage here is simplicity. So this is pretty easy to understand and implement. Here you have a linear flow of control, making debugging straightforward because you know about the flow and you know that this is going to stop till you get the response. So talking about real-time responses, now this provides immediate feedback, which is crucial for interactive operations like login or payment processing. So this provides you real-time responses. As I was saying earlier, debugging is pretty easy here. So this means that errors are handled in real time and retry mechanism can be implemented immediately. So easier error handling. Now this is well supported by popular protocols like HTTP, making it compatible with a wide range of tools and framework. Alright, now talking about cons here. So the sender is dependent on the receiver being available and responsive, increasing the risk of failure, also downtime. So here we have a tight coupling. Now we have limited ability to handle high loads as both parties must process request and response synchronously. So you will have scalability issues. Now high latency in the receiver can lead to poor performance or timeout for the sender, which we were talking about earlier. Now if the receiver is unavailable, the entire communication flow can break. So single point of failure. Now this requires both systems to allocate resources during the entire communication process. So this is pretty resource intensive. Now talking about asynchronous communication, here we have decoupling, which means that the sender and receiver operate independently, allowing greater flexibility and resilience. Now messages can be queued and processed at the receiver's pace, making it easier to handle spikes in demand. Message brokers provide durability, retries and delivery guarantees, ensuring messages are not lost. Here the sender doesn't wait for a response, allowing it to continue processing other tasks. So efficiency. Now this is ideal for systems requiring reactive behavior or where components need to respond to events in real life. Now talking about cons, this is quite complex because it requires additional infrastructure like message brokers or event system. Debugging is going to be challenging here. Now responses are not immediate, which makes it unsuitable for real-time operations because it is going to increase latency. Now eventual consistency models require careful handling of data synchronization and conflict resolution. Then it requires mechanism to handle failed deliveries, duplicate messages and processing guarantees. So you have to have some management in line. Extra effort is needed for implementing queue, retry logic and monitoring tools. So there is an extra overhead. Now let's talk about when to use which. Now let's say if you have a distributed system or a large scale event processing or maybe a system with high scalability, then use asynchronous communication because this is good for that. Now if you have operations requiring immediate responses such as user authentication, data fetching or payment processing, use synchronous communication there. Alright, now let's move on to the next question. What are the challenges of managing data in microservices architecture? So managing data, as we know, can be quite complex because of these reasons. Data decentralization, data consistency, data duplication, querying, data migration, performance and latency, data security, backup and recovery, monitoring and debugging, transaction management, scalability, data ownership, right? So a lot of things. I'm not going to explain each one of them, but let's talk about a few. So data decentralization. So the challenge is that each microservice typically has its own database to ensure loose coupling. That we know because we talked about key principles of microservices. So what happens is when you use own database for each microservice, this is going to lead to data silos. So coordinating data across microservices becomes complex. What is the solution? You can use domain-driven design to define bounded context, and you should rely on APIs or asynchronous communication for cross-service data sharing, right? Now, if you don't know about data silos, so data silos refers to isolated pools of data that are stored and managed separately, often inaccessible or incompatible with other systems or teams within an organization. So they typically arise when different departments, teams or systems use their own databases or storage solution without integration or sharing mechanism. Alright, now let's move on to next, data consistency. So maintaining consistency across multiple services is difficult, especially in the presence of network failures or distributed transactions. So microservices favor eventual consistency over strong consistency. So here the solution is use Saga design pattern for distributed transactions, and you can use event-driven architectures with message brokers to achieve eventual consistency. Right? Now data duplication. So services may need to duplicate some data to avoid direct database access from other services, increasing storage and synchronization complexity. So what you can do here to solve this, you can use data replication or materialized views when necessary, or you can employ event sourcing or CDC tools to propagate changes. CDC is change data capture. Now transaction management, this let's talk about. So transaction management can be challenging because traditional asset transactions are not feasible across distributed databases. So what you can do is you can use base principles here. Base means basically available, soft, state, eventual consistency. So implement compensating transactions for rollback in distributed workflows, and sometimes this gets quite complex, and that is why this is a whole another topic to talk about transaction management. It's not easy at all. Now monitoring and debugging, this is another challenging topic. So monitoring data flow and debugging issues in a distributed system is complex, and don't let me talk about logging right now. So what you have to do to solve this issue is to implement distributed tracing tools like Jaeger or Zipkin. So when you use centralized logging solution like ELK or Grafana to correlate logs across services, then your second logging issue is going to get solved, right? Alright, now let's move on to the next one. How do you debug high latency in microservices environment? Now this is a difficult topic to discuss because not many of us know about it, but let's talk about it because you can be asked this question. So there are certain things that we can do is that you can use observation tools like we just talked about, like Jaeger, Zipkin or AWS X-Ray. For centralized logging, you can use ELK stack, or you can use metrics monitoring like Prometheus, Grafana or Datadog, right? And what you can do is you should first try to find out which service or endpoint are experiencing high latency. Now you need to check if it is consistent or not. Now when you do that, you can use monitoring tools on that specific service or endpoint to check response times, error rate and throughput. Now there is no easy way. When we talk about this topic, there is no easy way, but you can analyze the entire request flow across services to pinpoint delay. So you need to figure out exactly at which portion of the code you are seeing the delay. So we need to look for slow services, like identify these database calls which may be causing this delay, or we can check if the latency is due to another third-party API call or maybe another external system. So there are certain common causes of high latency like your network issues, database bottlenecks, overloaded services, API timeout, excessive chattiness and misconfigured load balancer. So this is how you can try to fix or debug. Now let's move on to the next question. How do you approach end-to-end testing in a microservices architecture? So end-to-end testing means that you need to test the entire application and ensures that every microservice work together as expected. First, you need to find out critical flows. Then you need to validate interactions between microservices, APIs, or external system. Set up a test environment. Use a staging environment resembling the production setup. Here you need to include all microservices and their dependencies. You need to use configurations matching the production environment. So try to have a replica of your production, right? Now ensure that the test data is realistic enough and is consistent across services. Now test planning. So you need to have positive scenarios, you need to have negative scenarios to see if it is working fine in both of these two. Now you can automate this test using tools like Cypress, Selenium, or Playwright for UI level testing, and you can combine these with API testing tools like Postman or Karate for backend validation. Now you can also monitor logs and metrics like use ELK stack or Splunk to trace request flows, or you can check metrics using Prometheus or Grafana. And then you need to record and analyze failed test cases just to have more information out of it, right? So this is how you can do it. Now let's move on to the next question. What are the roles of service registers like Eureka, Console, or Zookeeper in microservices? So Eureka, Console, Zookeeper are service discovery and configuration management tools. So they help services locate each other dynamically, enabling seamless inter-service communication without hard coding service endpoint. So service discovery, as the name suggests, is a mechanism where microservices dynamically register their location with a central registry and discover other services via this registry. Now, talking about the basic difference between Eureka, Console, and Zookeeper. So Eureka purpose is to serve as a service discovery, but Console serve as a service discovery as well as configuration. Zookeeper is distributed coordination. Now the architecture behind Eureka is peer-to-peer client-server based architecture, but for Console it is just client-server, and in Zookeeper it is hierarchical tree-based architecture. Now, Eureka is simple and focused on service discovery, but Console is more complex but highly flexible. Zookeeper, on the other hand, is also complex and the ease of use is low level. Now, talking about health check, Console provides you advanced health checks, but Eureka gave you just basic health check, and in Zookeeper is quite limited. Now, scalability in both Eureka and Console is quite high, but in Zookeeper it is medium due to quorum requirements. Alright, so these are the differences between these three. Now, moving on to the next. How do you ensure fault tolerance in service discovery mechanism? Okay, so there are some strategies, best practices that we can use, like you can use redundant service discovery instances. So deploy multiple instances of the service discovery tool across different nodes or regions. So this ensures that the instances are synchronized using replication mechanism. So for example, in Eureka you can use a peer-to-peer architecture for replication, and in Console or Zookeeper you can use quorum based replication. Now load balancing and failover. So configure clients to query multiple service discovery nodes. You can use a load balancer or DNS failover to distribute client queries across available instances, and you can use fallback to the next available node if one fails. So here you can use client libraries with built-in failover support like Netflix Ribbon for Eureka, and you can configure DNS based round robin for Console servers. Now health checks for registry nodes. So regularly monitor the health of service discovery nodes, and you can use external health check tools or the native mechanism of the tool. For example, Console's built-in health check to detect and handle failures. Caching of service information. So clients should cache the list of available services locally to handle scenarios where the service discovery registry becomes temporarily unavailable. So this ensures that the cache information has a time to live and is refreshed periodically. So here you can use Eureka client cache service details by default, or you can use Console clients like Envoy or HashiCorp tools. Now you can use asynchronous communication because asynchronous methods for service discovery and registration avoid blocking client operations when the service registry is unavailable. For instance, leverage message queues or event-driven architectures. Alright, so now the next question is, how do you test the performance of individual microservices? So testing the performance of individual microservices involves various evaluating their responsiveness, scalability, reliability under different conditions. So first thing first would be to define your performance metrics. So in this, before testing, we have to establish key performance indicators like response time, which is your latency, throughput and error rate, CPU and memory usage, scalability and concurrency handling. Then we need to use performance testing techniques like load testing, stress testing, spike testing and soak testing. So you can also do latency testing and dependency testing. Then we should be using some tools for performance testing like your JMeter, Locust. For your API load testing, you can use Jaeger, Zipkin for distributed tracing. We can use Prometheus, Grafana for application monitoring, and Chaos Monkey for chaos engineering. Now when we say microservices, there is a conventional way, and then there are some specific cases that suits you better when you are working on a project. So if we know about our project, if we know about our own microservices, then first thing first would be to optimize the performance. So if let's say you have the legacy code written there, in that case you need to optimize the code, and if you have the inner queries written in the databases, in the database queries, in that case we need to reduce inefficient queries. We can always try to use caching like Redis to reduce the load, and you should be always using rate limiting and throttling in microservices because this is going to prevent overload from excessive request. And then we have our conventional ways that we have already talked about, like you can run your test in different environment and the tools that we have talked about, right? Now let's move on to the next question. How do you secure inter-service communication in microservices? So securing communication in microservices is very crucial to protect sensitive data and unauthorized access. So this will ensure integrity. So how to do that? So we can do mutual TLS for authentication and encryption. So we need to encrypt communication between microservices using TLS, which is transport layer security. We should ensure that our client and server both authenticate each other using certificates that we need to provide to each other. Now to implement this, we can use a service mesh, or we can configure Spring Security with MTLS. Now OAuth and OpenID connect for authentication. So OAuth issues access tokens that microservices use to authenticate requests, and this is very much same to what we have done, or we must have done with RESTful web services as well. Now OpenID Connect extend OAuth to handle user identity. So here we can use Keycloak, Okta, Auth0, Spring Security to enforce security. Now JWT for token based security. So microservices exchange JWT tokens for authentication and authorization. So JWTs contain claims and are digitally signed for integrity. So to implement this, we can issue JWT using an authentication server like your Keycloak, Auth0, and then we can validate JWT in Spring Boot using your Spring Boot starter OAuth2 resource server dependency. Now these were the major things that we should be doing, and then for centralized security we can have API gateway. So API gateway acts as a security layer between clients and microservices. So whatever common thing that we wanted to do for each and every microservice, in that case we should be doing everything on API gateway, so that we don't have to handle everything individually. So here we can handle authentication, rate limiting and request filtering. So to implement this, we should be using Spring Cloud Gateway, Kong or Nginx. Alright, now let's move on to the next question. How do you implement rate limiting and IP whitelisting in an API gateway? So implementing rate limiting and IP whitelisting in an API gateway helps protect your microservices from abuse, DDoS attacks, and unauthorized access. We just talked about this just before this question. So to implement this, like I said before, we can use Spring Cloud Gateway, Kong, or Nginx. So rate limiting in API gateway controls the number of requests a client can send within a given time frame. So here in this you can see the step-by-step implementation using Spring Cloud Gateway. First thing first is that you need to add Redis dependency. Afterwards, we need to configure rate limiting in either your application or properties or YAML. This example is specifically for YAML. So here you can see that in the filter I have a request rate limiter where I am actually limiting the request per second to 5 and burst limit to 10. Then we need to define an IP based key resolver. So here in this example you can see that there is a bean separate for IP key resolver. Now how does it work? So replenish rate is your maximum request allowed per second, which we have set in the YAML file. Then we have our burst capacity, which is extra request allowed in short burst. Key resolver is basically going to use your client IP to track rate limits. Alright. Now similarly you can do it for Kong API and Nginx. Now IP whitelisting in API gateway, so this allows access only to specific IP addresses. Now if we go with Spring Cloud Gateway, first thing first is that we need to create an IP filter in the API gateway. So in this example we can see that this filter blocks requests from non-whitelisted IPs. So in the variable allowed IPs you can see that I have listed all the IPs that should be allowed, others should be ignored. Similarly, we can do it for Kong API and Nginx. Alright, so let's move on to the next question. How would you implement authentication in a microservices architecture? So implementing authentication in a microservices architecture requires a centralized authentication mechanism while ensuring each microservice remains independent and secure. So here the most common approach is using OAuth 2 with OpenID Connect, which we already talked about. Then you have your JWT tokens, which we again talked about before, and finally your API gateway. Now let's move on to the next question. What are circuit breakers and how do they help in microservices? So circuit breaker is a fault tolerance mechanism that prevents cascading failures in a microservices architecture by detecting failures and stopping repeated failed requests. So this ensures that a failing service does not cause system-wide slowness or failures. So if you don't know, circuit breaker is also a design pattern in microservices architecture. Now why do we need circuit breakers? So first is to prevent service overload. So if a dependent microservice is slow or down, the circuit breaker stops unnecessary requests. Second is to improve system stability. So it is going to avoid cascading failure by failing fast and preventing retires to a failing service. Third is to enhance user experience. So this is going to return a fallback response instead of making users wait for timeouts. Now there are certain states in your circuit breaker design patterns. So it operates basically in 3 states. So we have closed, open, and half open. So closed means that the service is healthy and requests are allowed. Open means that service is unhealthy and requests are blocked for a cooldown period, which you are going to define. Then half open, which means that a few requests are allowed to check if the service has been recovered. So the flow is going to be like, if the request succeed in half open state, then circuit closes, which means that your normal operation is going to get resumed. But if the request fail, in that case circuit reopens and then requests are going to be blocked again. Now how to implement this design pattern? So there are some very popular tools like Resilience 4J, which is supported in Spring Boot 3+. Then you have Hystrix, which is Netflix basically, and again deprecated. Then you have Istio Service Mesh, which is Kubernetes. Now my preferred way would be to go with Resilience 4J, and it is supported with Spring Boot 3+. So you just need to add the dependency for Resilience 4J in your pom.xml. Once you do that, you have to add a certain property to configure circuit breaker in your YAML or property file. So here you can see that my circuit breaker properties are these, where I have sliding window size, which is going to track last 10 requests. Then I have failure rate threshold to 50, which means open circuit only if 50% of the requests are failing. Then we have wait duration in open state, which is 5 seconds, which means that you need to wait for 5 seconds before you retry. Then we have permitted number of calls in half open state, which is 3, which means that you are going to be allowed 3 test requests. Now how to use circuit breaker? So here you can see that there is a service, order service, and here I have a REST template. So what does it mean? So here I have a get payment and I have a fallback get payment. So if the payment service fails, it could be because of timeout or maybe certain error, then the fallback method runs instead. So the second method is going to run and it is going to return payment services down, please try again later. Now if 50% of requests fail, which is coming through your failure rate threshold, in that case the circuit opens. Now after 5 seconds it allows 3 test requests, which we have mentioned in the properties, but if it is successful the circuit closes, otherwise it stays open. Alright, now let's move on to the next question. How would you use patterns like retry, fallback and timeout to improve resilience in microservices? So resilience patterns help microservices recover from failures, handle timeouts and provide alternate responses instead of crashing the entire system. So we talked about circuit breaker design pattern just now. Then we have retry pattern, timeout pattern and fallback pattern. So retry pattern automatically retires a failed request. Timeout pattern cancels a request if it takes too long. Fallback pattern provides an alternative response if a service fails. So when we say automatically retry failed operations, so it could mean your transient failures like network timeouts and rate limiting. So to implement this, we just need to implement a dependency, which is again your resilience 4J. Then in the application.yaml you can provide these 2 properties, max attempt and wait duration. Then you need to apply a retry to a service. So here we have retry annotation where we have name and a fallback method. So again this works like your circuit breaker design pattern. So if the inventory service fails, the request is retired 3 times. If still failing, the fallback method runs instead, right? So I hope the difference is clear. Now timeout pattern cancels a request if it takes too long. So this prevents a single slow service from blocking the entire system. So here in the properties or YAML file, you need to define these 2 properties: connection timeout to 2000, which means 2 seconds connection timeout, read timeout to 5 seconds, which is again a read timeout. So you can modify these 2 properties according to your relevance. Now you need to use Feign client with timeout. So here if you see, I have a payment client where I have a Feign client name with payment service and a URL where I have a get mapping as well. So if the payment service takes longer than 5 seconds, the request is cancelled. So this prevents slow services from blocking the main application. Now you have fallback pattern, which provides an alternative response when a service fails, which basically avoids a complete system failure. So here again you need to provide these 2 properties in your YAML or properties. So you have failure rate threshold and wait duration in open state. Then you need to apply circuit breaker with fallback, which we have talked about before. And also you can combine all these patterns in one microservice, which we again have talked about. Alright, so this is it for this question. Now let's move on to another one. what are some best practices for logging and monitoring microservices? So in a microservices architecture, these two comes very crucial for debugging and performance optimization and also fault detection. So first thing I would suggest is to use centralized logging. Why? Because each microservice generates logs, and managing them in a separate location makes debugging difficult. So here the best practices would be to use a centralized log aggregator like your ELK stack, Loki. So here you need to attach trace IDs to each request for end-to-end tracking, and you can also use structured logging, like you can use JSON format for easier querying. So second would be your distributed tracing. Because microservices involve multiple requests across different services, so distributed tracing in a distributed architecture helps track requests from start to finish. So best practices would be to use OpenTelemetry, Jaeger, Zipkin for tracing, propagate trace IDs across all microservices using HTTP headers. Third would be your monitoring and metrics, because continuous monitoring helps detect performance issues and prevent failures. So you can use Prometheus, Grafana for metrics visualization. Also, we should be monitoring CPU memory, request rates, error rates, and setup alerts using Prometheus. Now, error logging and alerting, so detecting and fixing issues in real time is critical. So we can use tools like Sentry, Datadog, or ELK stack for error alerts. We can set up Slack or email alerts for critical errors. We should be monitoring HTTP status code, error logs, and slow queries. Lastly, API gateway logging and monitoring. So why? API gateway handles all the requests, and logging them ensures security and performance tracking. So we should be enabling logging at the gateway level. So for example, you can use Spring Cloud Gateway, Kong, Nginx, and monitor request latency and success, failure rate, and response size. And also we should be implementing rate limiting and security logging. Alright, so this is it for microservices, and we are done with this video. So if you have seen this video till now, thank you very much. Don't forget to like, share this video, and subscribe to my channel. So in the next video we are going to talk about REST API, so stay tuned for that, and till then, stay happy, keep learning, and bye bye.